All right, people. Chapter 2, sections 2, 3, and 4. What questions do you have for me on separable equations, linear equations, and exact equations? No, but I can either do 19 or 21. Let's take a look. 2.2, number 20. Oh, I see what's bugging you. Let's do 19 since it looks fairly similar. Okay. Yeah, that looks disgusting. But the thing that will help us the most is if I can separate, right? Well, that means I should try and factor that stuff. So let's factor numerator and denominator by grouping. I'll factor in pairs. There's an x I can pull out here. X times what? Just out of the first two. So what could I do with these two to make that a y plus 3? And then down here, under the same vein, if I pull out this, what becomes the thing here? Oh, so this is x minus 1, y plus 3 over x plus 4, y minus 2, and that's dy dx. So I'll put all the y terms on one side by multiplying by the reciprocal, and I'll put the dx on the other side. Did you get this far at 20? Okay, so the question is, how the hell do I integrate this? Okay, there are two different ways to integrate this. One is to actually try and do the division. Do you remember doing a long division? Doesn't it just suck? Yeah, let's not do it that way. So I look at this and I say the top highest power in X and in Y is the same, right? So maybe I can fudge the constants. It would be so much nicer if this was Y plus 3 on top and Y plus 3 on bottom, because things would cancel. So I look at this and I say, well, Y minus 2 can be written as Y plus 3 minus something else. What's the something else? Aha! So I'm going to write this as y plus 3 over y plus 3 minus 5 over y plus 3. What do I get if I try and do the same thing over here? I write x minus 1 as x plus 4 minus something else. Again. But these are ones. And these are ones. The fractional term now is an ln after a u substitution. I now know how to integrate this. It's not the calculus part, it's the algebra that sucks. A recommendation. After you've done them by hand, do them in Wolfram Alpha to check. Yes.
For 36, it says use a graphing utility on the graph the solution. Do we need to put that in our?
If you've done it on the grapher in or in slopes on the computer, you just screenshot that, print the screenshot. You don't have to redraw a damn thing. Don't make a second drawing, just screenshot and paste. Apparently, I'm having a drinking problem. More questions. Technically, I can actually I can draw the picture without solving it if I do it in slopes.
For 2.3, for one similar to you have to solve for both like conditions the piecewise function.
Yes, unfortunately. Because if we go back and look at example 6, once we have a piecewise function like that, we're really going to have to do there it is with the 1. And then when we solve this one, there it is with the 0, the two different pieces, right? I get this equation, and then I get this equation. So my answer is a piecewise function. You're looking at me like I'm a space alien, man. So the problem has these two pieces, right? So we're going to do two separate solving. Here's where we do it with 1. Here's where we do it with 0. This piece is only good when x is bigger than or equal to 1. I'm sorry, between 0 and 1. This piece is only good when x is bigger than 1. So when I put the solutions together, I have to keep those with it.
Okay. And then that would also be the.
Well, do we have an initial condition in that one? Then yeah, I'm going to use that to make the initial condition. And yes, that'll help me with the domain of definition. Right? I'm sorry, didn't you say it was 40?
Yeah.
Okay, talk to me.
So then when you're solving, I just got mixed up when solving for C in the second part.
My goal in the second part is to solve so that the graph is continuous. So when you solve the first one, you're going to know what the value is at 1, right? Because you'll be able to plug in x equals 1. So use y of 1 equals whatever the value is there to solve as the initial condition for the second part. So once you've got your first part of the solution, you go to the furthest edge you can find the y value, use that for the initial condition for the next part. That way your two pieces come together. And most of the time that works. When it doesn't, it's because we have some sort of asymptotic behavior at that juncture, which we don't in this case. More questions? Oh, excuse me. Yes, Jason. 2.330. Okay, so the problem with this one is that there are no frickin' numbers. All that means is that we're going to treat those three like they are numbers. Let's take a look at 29 right above it, okay? So L d I dt plus Ri equals E. E of I of 0 is I0. And all these things are numbers. Now, if you wanted to, you could just plug in some numbers here and then try and undo that when you were done. I think that's more trouble than it's worth. L is a number. L is the number next to my derivative. This is the section on linear equations, so I should be using an integrating factor routine, which means it needs to be in standard form, which means I need the derivative all alone, right? So I'm going to divide by L. di dt plus R over Li equals E over L. With me so far? R over L is a number, but it's in the spot for P of T, right? So that's where I get my integrating factor from. Integrating factor is E to the integral of that thing. But that thing is a number. What's the integral of a number? Number times variable, right? So it'll be R over L times T. So I multiply that through everywhere. Isn't that just disgusting? This is an integrating factor problem. This is a linear differential equation. The left-hand side's a product rule. It's the derivative of a product rule. Derivative of the exponential, derivative of the I and the I, right? Derivative of the first times the second, derivative of the second times the first. I've got exactly the pieces I need for that to be product rule, which means this side is the derivative of what? It's always the same things. E or and on the left, I just have number e to the number t. To get rid of the prime, I integrate with respect to t. Now here's the part where I have to remember how to do e to the number t. What's the integral of e to the 2t? That's the derivative. 1 over 2 e to the 2t. If I had e to the 3t, it would be 1 over 3. If I had e to the 7t, it'd be 1 over 7. It's e to the r over L. This is a number. I put it out front. The integral of e to the number t is 1 over the number e to the number t plus c. See, Jack, this is the problem. They're disgusting, ugly-looking, formulaic garbage full of letters everywhere. I just have to remember, these are numbers. Treat them just like they were a 5. What happens between these two numbers? It ends up being e over r. Now I want I all alone, right? So I divide by this. What happens here? Ta-da! That's a really bad looking E. I apologize. But wait, there's more. I was given an initial condition, wasn't I? My initial condition was that I of 0 is some number. Right? So on the left, I'm going to get I null. On the right, I'm going to have E over R plus C times what? This is a T value. So to be E to the which is just 1. Hey, wait a minute. That means that C is I0 minus E over R. That's my formula, and that's exact. That works for any resistor, any capacitor, any current, and any battery E. So this applies to circuitry, right? That's where this came from. This is one of Kirchhoff's laws. And this is about a circuit that has a battery in it, a resistor in it, and a light in it. And what I want to know is about the current in the wire. So if you tell me how much current is in the wire when we start, you tell me the size of the battery, the power of the resistor, and the load of, I don't know, that's usually designed to be a filament like a light bulb. So I need to know this number, this number, this number, and how much current's in the wire when I start. And then you can tell me what the current is through this wire at any point in time. Why would I need to know such a thing? If I grab the wire and it's hot, I'm dead. How much current's in the wire? But maybe, maybe not. Maybe it's just a little bit of a jolt and I go, oh, don't do that. Right? But I can tell you the current is at any point in time. And if I know that that current happens to be high enough to overheat the load, then all of a sudden I'll know, hey, this lamp's going to burn out much faster than I wanted it to. Or maybe the resistor is too high and it's not going to let enough current through and the light's barely going to light at all. So I can judge all of those things based on my knowledge of what this current function looks like. How fast is the electricity moving through this circuit? Now, in the problem you're asked about, that's Newton's law of cooling. That's about an object being placed into a temperature. Give me the actually differential equation. D capital T, D little t equals. And then there's an initial condition, T of 0 equals T sub 0. So what this says is that the change in temperature of an object is proportional to the difference in temperature between the object and the surrounding medium. And the starting temperature is some number. You take a can of soda out of the fridge and put it on this table. How cold's the fridge? Yeah, well, what if I go to your dorm and I open your fridge, what's the temperature in your fridge? Okay, so 38 degrees. This room is 68 degrees or 70 degrees, right? I set that can right here on the table. That's 72 degrees. That's 38. There's some constant, I don't know what that constant is yet, that tells me how much cooling or warming will happen. At some point in time, your soda is going to reach 50 degrees. When? Once I solve this equation, I'll be able to tell you exactly what's happening. At some point, it's going to be 71 degrees. Will it ever be 73 degrees? Because this room is only 72. On the other hand, if I take the soda that's been sitting in my car all day, that's still closed, and I put it in your fridge, Well, the starting temperature might be 85 degrees. And the surrounding is now 38 degrees. I can have a temperature that falls over time. They're just numbers. Which numbers depends on which situation I'm in, right? I take the turkey off the counter, put it in the oven to bake. Surrounding temperature, starting temperature. I hope I can figure out this number by how long it takes my damn turkey to cook. Otherwise, we're eating Chinese food for Thanksgiving. Does that make more sense? The whole idea of doing this all in letters is not to piss you off, but to give you the most general version of the scenario. And if I get used to treating these things like they're numbers, then I can apply this same differential equation to just about any situation. I mean, we did this back in Calc 1. We were talking about a pendulum, and it had an amplitude and a frequency and oscillating. And I think the equation out of the textbook, I'm trying to pull this out of my ass at the moment, so I might not get all the letters right. I think it was A sine omega t plus delta. And then you had to take the derivative of that, and you knew that A and W and delta were numbers. What's the derivative with respect to t? And what did that mean? And that was about the velocity on my pendulum. Oh, okay. Angular frequency is how fast it's moving back and forth. Delta is where we started from. A is amplitude. And when we did that problem in Calc 1, y'all hated me then. Letters, then numbers. As a matter of fact, we'll see later in chapter 3, we'll see a model for radioactive decay, where instead of just decaying into one thing, the atom decays into two different things. And the proportions are different. I kid you not, I taught that problem in this class. And at the very same time, in that glass room across the hall, Dr. Miller's thermo class was using the model we came up with. The very next week, when I walked over to observe her class, because she asked me to, they were working on this problem because she'd given me the notes in advance. And I'm like, wait. And I opened the Diffie book and I showed it to her. And she's like, whoa. They didn't know where the equation came from. They were just working with it. I'm like, dude, it came right from here. And 3 of the people in this class were in that one. It's so much fun. Real world stuff. Okay, I ranted enough. More questions. Yes.
So, in 2.4, I got stuck on an integral. You help me with that?
Yeah, talk to me. What's the integral you're stuck on?
So, on the equating factor, so my new equation is, difference is 1 plus x to the negative third times parentheses x squared plus y squared minus 5. Then that subtracted is y times 1 plus x quantity to the negative.
-2. There are some dy's and some dx's floating around here. Otherwise, you're already done integrating.
Oh, the x on the left one.
Right. So we're going to integrate 1 plus x to the -3, x squared plus y squared minus 5 with respect to x. Yes? That's gross. But it's less gross than you think it is. I'm going to break this up into 3 separate pieces. You know, I really didn't even need to rewrite these two, the last two, because they're a U substitution, aren't they? It's just this first one that's the problem, isn't it? I could, but if I did that, I'd then try and do a U substitution again, right? And that just doesn't sound reasonable because then I have an x cubed and an x squared and an x on the bottom, and I only have an x squared on the top, right? I think this might actually be. No, if I do a partial fraction, I think I end up in the same place. X squared over 1 plus x cubed. I have an idea for this one. I'm going to do a weird substitution. I know that's always quite questionable. For this one alone, I'm going to let u equal 1 plus x. But then, well, which is the same thing I did over here, right? But then to do this one, I'm going to rewrite this as x is u minus 1. So what happens to this equation? Just this one, x squared over 1 plus x cubed dx. That becomes, oop, forgot my parentheses. That becomes u minus 1 squared over u cubed du. And now instead of multiplying out the bottom, we get to multiply out the top. That'll be easier to integrate, won't it? Yay, it just became all power rule. Whew. You're shaking your head at me. You know the worst part? Chapter 5, section 5. There's an example that does exactly this. I'm teaching Calc 1. I've been looking at those notes. Yeah, I used to know how to do that. Long time ago in a galaxy far, far away. Again, I'll say the same thing. Once you finish this problem, shove it into Wolfram Alpha and check it. Let's make sure that if you were to just type that in versus what you get out at the end after doing all of this, make sure we get the same thing both ways. If not, what did we do differently? That's when you come to all stars go, what the hell? We figured out together. Better? Kinda. It's amazing.
What was this problem for?
This was, you said it was 40. Oh, and by the way, since I'm integrating this one with respect to y, that's going to be really easy. Hit me again. Oh, dun-dun-dun. No, 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 no. Metallic and clear. Yes, ma'am.
So, do the interval that
Yes.
marks out. It's just formulas, this is the bond, right, so I just want to know the person.
If we don't have an initial value, yes. If we do have an initial value, then we have to make sure whatever piece of the domain contains my initial value is the section I'm looking at. And remember, as we were doing the solving, we might have divided at some point, so I would have to take that into account. So back in the one we were doing, ask me about, I'd have like, oh, wait, I can't have x equal -4, I can't have y equal 2. I created this part of the problem is already set up with those sorts of asymptotes. And then when I do this, I also lose y equals -3 because I have another division here. So I end up with 3 distinct asymptotes, 2 that are horizontal and 2 that one that's vertical. So I need to keep track of those in my solution. But this one didn't have an initial condition, so I wasn't worried about it there. Oh dear. Oh. In which section? 2.4. So 34 or 35? Which one do you think is uglier? It's 34, 5 it is. That's the first one. You said 34 or 35, so we'll do 34. So x plus y plus 1 dx equals x plus 2y dy. Yes? Yes. X plus 2y dy. First thing I have to do is put it all on one side. It should be m dx plus n dy equals 0. Did I copy things down wrong? Yes, I did. Plus equals 0. So that should be a plus, not an equal sign, and the equal 0 goes over here. Thank you. Good catch. Bad, Joshua. Copy the problem down right. If you copy it down wrong, everything up. Okay. M, Y, N, X. My is 1 times x plus y plus 1 plus y times 1. So that's x plus 2y plus 1. And x is just 1. Those are not equal. I am a sad person. So I need an integrating factor that looks like something all in x or something all in y. And my first reaction is I'm either going to take my minus nx or I'm going to take nx minus my, right? So let me just pick one at random. My minus nx is going to be x plus 2y, isn't it? That minus that. And then if I divide that by n, how do I remember which one I'm dividing by? I always divide by the one on the end here. That's 1. Now, here's where I need you to look something up for me. Is this the mu x or is this the mu y? I need to know which one it was based on the formula. In the section, we said, hey, if my thing is in terms of just x, I can do it this way. If my thing is in terms of just y, I can do it that way. According to this formula right here on page 70, if it's my minus nx over n, I should be looking in terms of x. So that means that my integrating factor should be e to the x. Mu is e to the integral of 1 dx. If I'd done it in the other order, I would do the integral with respect to y. If this is a function of x alone, well, 1 is definitely a function of not y. If this is a function of y alone, here's my integrating factors. So I know, since this was a factor, I can multiply by e to the x. 2 zoomed in. There we go. So that's e to the x. So that means that my new equation, new piece of paper, should be x plus y plus 1 e to the x dx plus x plus 2y e to the x dy. That should, underline that word, should be exact. My is x plus 2y plus 1 multiplied by e to the x. I multiplied that y through so that I could take the derivative easier. That way I only have two pieces. And then over here, this is n, so I need to look at nx. Well, now both parts have x in them, so that's the derivative with respect to x here is 1 e to the x plus x plus 2y. Take the derivative of the other piece, that's e to the x. Hey, look, that's e to the x times 1 plus x plus 2y. Those match. It worked, master, it worked. Yes, Igor, you fool. Sorry, wrong monster. Or Renfield. Granted. So, how do I find the function that I want? I integrate m with respect to x. I integrate n with respect to y. Integrating n is going to be a lot easier because there's only one y. Integrating m is going to be harder. But now I know it should work out. Everything should be balanced and reconciled when I finish these integrals. Is that better? Doesn't that just suck? Now, I literally flipped a coin as to which one in my head, whether I should do my minus nx or nx minus my. But I looked at the two that we were working with, the two pieces, and I said, hey, look, this is almost that, isn't it? So if I divide and low, I can subtract. So I kind of said, oh, it'll be easier to do this one minus that one. If I'd done it the other way, I would have gotten negative x minus 2y, but it would have been divided by this, and that's much uglier, isn't it? So I kind of, since it really is a toss-up, I kind of went, one will look like it's going to be easier than the other, and lo and behold, it was.
How did you
How'd you get an X, like a. Or one, the X?
Oh, derivative of the first. I'm taking my derivative in terms of x, so that's a 0. I just get 1 times the second. Derivative of e to the x is e to the x times the first. I just did the product rule. That's why I multiplied through over on m, so I only had 2 pieces to do the product rule on.
Oh.
Because I am a lazy mathematician and I hate doing triple product rule. It's annoying.
Would it be easier just to multiply, like,
In this case,
Yeah.
absolutely. But then I would have x e to the x, wouldn't I?
Yeah.
And I'd still need the product rule. So do I gain anything by multiplying that out? Okay, but then I still have to compare what I get over here with what I get over there. Still need to do that comparison. But the result of doing our integrating factor did give us an exact equation. We have an exact equation. We do our partial integration. We know what to do. I may not like doing it, but I know what to do. There's a bad joke about an engineer, a physicist, a mathematician who fall asleep in a hotel. 3 different rooms that all have a central column. So you have like 3 rooms with a common corner. And the electrical outlet in that corner catches fire. And so all of the 3 rooms are on fire. And the engineer wakes up. Sorry, the engineer wakes up, sees that the room is on fire, goes to the shower, yanks down the shower head, the handheld, and sprays down the room, and the fire goes out on his part. He goes to sleep in a soggy room. The physicist sees that the room is on fire, eyeballs it, goes over to the bathtub and fills up the trash can and goes, psst. And that's the only part of the room that's wet, and he goes to sleep in a dry bed. Mathematician wakes up, sees the fire, sees the shower head, sees the trash can, goes, a solution exists, I can go to sleep. I know what to do. I may not like it, but I know what to do. So this is due on Friday. If you've got questions between now and then, email me, stop by office hours tomorrow, either in the morning or the afternoon. Otherwise, I will see you all then. Have a wonderful rest of your day.